computer. All right. Welcome back, everybody. It's Monday, February 28th, 11 a.m. here at Texas State. That's great. Thank you for showing up. More people today than usual. That's wonderful. Saw that COVID numbers are going down in San Marcos. It's still a little higher than the rest of Texas, but we're doing okay. As we get better, we'll see more and more people around us, I bet. Okay, so where we left off last time, we were talking about a very powerful way to draw structures to show you how the different groups interact, and that was called the Newman projection. And in the Newman projection, when we draw those, we look down two carbons. We put one of the carbons in front with the lines meeting in the middle. The carbon in the back is represented by that circle, and then the things coming off it are the three things bonded to it. Now, that's those three other things bonded to it besides the carbon-carbon bond we're looking down. So we saw that there was different types of interactions. There is an eclipsed, a gauche, and an anti. And we figured out that the anti configuration is our lowest energy configuration because it has the fewest things butting up against each other. Okay, so that is really cool. But what happens if you lose the ability to rotate around that sigma bond? If we lose that ability to rotate around the sigma bond, we have things like a pi bond, or we can also have rings. When we have rings, it doesn't have full capability to rotate around. And so we end up having what we call ring strain. Okay, so where are my pencils? Hiding in my jacket. So we have ring strain. Okay, but why? Okay, so let's draw a nice little ring here. Let's do, our smallest ring we can make is 3 carbons. And we learned that that's called cyclopropane, right? Because it's 3 carbons, cyclopropane. And what we have with this is we have rings that aren't quite 109.5, right? We want 109.5 because that's what our hybridization is. The angle in here is 60 degrees. Okay, so there's a lot of strain there to keep it from that 195 to get it down to that 60 degrees. And so when we see that strain, it actually makes it less stable. Okay, so that means that the cyclopropane is actually less stable than cyclobutane because this is a little bit bigger angle. This is 90 degrees. Still not 109 degrees, but it's 90 degrees. And then if we move up to something like cyclopentane, we now have 108 degrees. So that's pretty close. Not perfect, but it's pretty close. 60 degrees. And then if we go all the way up to something like cyclohexane and we draw it flat, that's 120 degrees. Okay. So none of them are ideal. The closest one we have is cyclopentane to having the least amount of ring strain. Okay, so that means that they're not exactly flat like we drew them. The cyclopropane is flat because that maximizes its way. It has no, it's got 3 points and that makes a plane, so it is flat. However, cyclobutane, to try to get away from getting that 90 degrees, try to get it a little more than 90 degrees, it actually is puckered, okay? So if you look at it on the side, we see it puckered. It can flip back and forth between the two, okay? So again, these do have 3-dimensionality, but they don't have that 3 rotation we saw in the straight chain hydrocarbons. Now, if we go to cyclopentane, remember it was 108. It was pretty close to 109.5. And so it has a slight pucker. We call it the envelope because 4 of the atoms are in the same plane and one of them pops out. Okay, so I'm going to skip cyclohexane here for a minute and then go to cycloheptane and cyclodecane. Notice that these are rings as well. And notice how they can now, instead of being perfectly flat, they're trying to get to that zigzag configuration. So we're starting to see more zigzag configuration in those because they have enough room to be able to get closer to that 109.5 degrees. Okay, so what about cyclohexane? Well, when I drew the cyclohexane, I drew it flat like this, we saw that it was 120 degrees apart right here. Okay, and so if we draw that flat again as, no, I have misplaced my Apple Pencil, so I can't just double tap. So if we have it drawn in perspective, so these three bonds are coming out at us, the others are going behind us, and we look at where those hydrogens are. We have a hydrogen here and a hydrogen here, but then we have a hydrogen here and a hydrogen here. So in this configuration, in its flat configuration, it's actually eclipsed, right? All of the bonds are eclipsed on each other, okay? And it's 120 degrees. So it definitely doesn't like to do this. What it's going to do is it's going to try to go into a zigzag configuration. And it turns out cyclohexane, when it's drawn on its side like that, tries to achieve this 109 degrees by moving around. Oops, I drew one of the hydrogens wrong. By moving, by just rotating that sigma bond a little bit to get them into that gauche configuration. Okay, just by going to that, it actually gets it back to the angle now is 109.5 degrees. So what does that mean about the ring strain of cyclohexane? If it can move such that it has 109.5 degrees, it has no ring strain. Okay, so it has the least ring strain of any of the rings, because as you get bigger, you have a little bit of trying to get them all right. So of the small cyclos, that is the one with the least amount of ring strain. So the most is cyclopropane because of the 60-degree angle, the least is cyclohexane. So when we look at this, all of the hydrogens are staggered and the carbons are gouged to each other if we look down a straight line and drew a Newman projection, which we will do. So, okay, so if that is a way to draw our cyclohexane, let's draw it in that configuration. That configuration has a name. It's called the chair configuration, okay? So let me draw that chair configuration for you one more time. And the easiest way to draw a chair configuration is you do two parallel lines. Oops. Two parallel lines, two parallel lines, and then two parallel lines. And that draws your chair configuration, okay? So the ways we call it a chair configuration is if I draw it this way, where this is up and this is down. So this is like the head of the chair and this is like the foot of the chair. Now, when we draw this way, we have to look at it as, okay, so let's see how these bonds are arranged by looking down one of these bonds. So I'm going to redraw that chair configuration by rotating this around by about 120 degrees. So that's going to give us two carbons down here. It's going to give us one carbon behind the other one here, and then this one up here. Okay, so each of these represents two carbons. And if we draw it as a Newman projection, we're going to have the circle here for the one in the back, right? The carbon in the back is the one that has those two other bonds going to the back carbon. So that's why they're there. And the one in the front here has two hydrogens right here. And this one has two hydrogens right here. And that means that there's a hydrogen back here and a hydrogen back here. I'm sorry, the hydrogen's in here. So looking down this configuration, we see that we have two carbons in their gauge position, and the hydrogens are in between all the other systems. So we can see that we have not only no ring strain because of the 109.5 degrees, but the only interaction we have is the carbon-carbon gauge interaction. So it's actually fairly stable in the system. Okay. So if we were to look at, okay, yeah. So moving is that the same then? Let's look at that cyclohexane again, redraw it. And again, draw it with parallel line, parallel line, parallel line, and then two off like that. So not all of the positions of the atoms attached to the ring are the same, okay? We have two types of positions. And the way I like to look at it is, if the cyclohexane was the Earth, and this was its axis, we have hydrogens or attachments that are in line, parallel with the axis. We call those axial hydrogens or axial attachments, okay? Because they're in line, they're parallel to that axis there. Now, if that was also a planet, and what would be around the outside? The equator, right? So that means we have the equatorial ones are the ones pointing out away from the center of the ring, away from that axis. So we have axial hydrogens and we have equatorial hydrogens. Okay, so, and they're not exactly the same. And you're saying, well, okay, well, I have all these hydrogens and I have a chair configuration. Is it fixed in that position? And the answer is no. We can actually flip it from one chair to the other. Okay, and so the way we do that is you can start drawing your configuration in either way. So I'm going to do it right here. We're going to draw it like this. And to make this chair into the other chair, we actually go through I'm sorry, it's not, it's in equilibrium. Right here, it'll go through the point where we're going to pull this carbon up. And if we pull that carbon up, we now have something that looks like a boat. Okay. Let me redraw for even more clarity. Right there. We're going to pull this one up right here. And if we pull that one up, we end up with a configuration that looks like this. This is the boat configuration. Okay, now if we take this side and pull it down, we have the other chair conformation. So we've gone from one chair conformation to the other chair conformation. Okay, and when we do that, we go through this higher energy state here. The reason that's a higher energy state is because if we looked at our structure when it's in this configuration and we added some hydrogens, I'm not going to add them all, I'm just going to add the ones here. We see that we have these positions here, these two hydrogens are getting close to each other. Those two hydrogens are like the flagpoles on the front and the back of the boat, which is why we call them flagpole positions. Okay. Now, if we draw the Newman projection again of this, we're going to look down this bond here, these two bonds here, and draw that Newman projection. We have one CH2 up here. We have a hydrogen and a hydrogen, hydrogen and a hydrogen. Then we have our back one. We have a CH2 here that's overlapping. And we have a hydrogen, 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 hydrogen. See how these are all eclipsed now? So we went from something where they weren't eclipsed, they were all gauche, to all eclipsed. The hydrogens are eclipsing hydrogens and the carbons are eclipsing carbons. So it's a higher energy state. Okay, so that being said, we looked at our nice little energy diagram that said, oh, well, if we take our Newman projection and rotate it, the energy changes, right? So how does it change as we go from boat to chair to everything else? Well, it turns out it's pretty significant. The first thing we have to do is we have to start in our first chair, right here. And that's the lowest energy state, right? Everything's 109.5, everything's gauche, which is the lowest energy it can get. The first thing it has to do is flatten out one of those corners. And doing that turns it kind of almost into an envelope. We call that a half chair. That's actually the highest energy conformation for this because it has as many of the carbons eclipsed as it can. That's why it's the highest energy. Then it kind of twists a little bit so that it can get into a configuration where it can actually pop it up. And then when it finally does pop it up to where it have it eclipsed, that's where we get the system where the two flagpole hydrogens exist, the flagpole positions exist. Notice the twist is slightly lower in energy. The twist is slightly lower in energy because of those flagpoles starting to hit sterically against each other. Then, of course, it can twist a little bit more, continuing going in the same direction through the half chair, and now we're in the opposite chair configuration. So we have to go back and forth. These can go back and forth between the boat and the chair. In cyclohexane with no substituents, it can do it at room temperature, just constantly flipping back and forth. Okay. So questions about that? Okay. So if we can flip back and forth there, when we have hydrogens, and there's no real difference between the one chair and the other chair, what happens when you put something on there? Oh, did I? Hang on. I'm on a, there we go. I'm gonna actually take roll right now before I forget. So many people came here to see me. I'm gonna give you credit. Things are going down. So. Okay. So we're going back and forth between these two conformations, and there's no difference if they're all hydrogens, because hydrogens are all the same size. But we do know we have two different types of hydrogens. We have the axial hydrogens, the ones in going through the center, going parallel to each other, and we have the equatorials, which are fixed on the outside. So what if we add something to the ring to make it a little bit less like hydrogen? So let's take this and add a methyl group to it. Okay, so we want to go CH3 and an H here. Okay. So in the case of the substituent, you want to actually have one of the chair conformations is actually going to be favored over the other. Okay, so in this drawing here, we have the hydrogen here is in the axial position, and the methyl group is in the equatorial position. What if we flip that? So we're going to pull this one up, flip that one down, and so that's going to turn into. And now we have, no, that's, is it drawn right? Yeah. So now we have, no, it's drawn wrong. That's, that methyl group. Oh, okay, I drew it wrong. Let me redraw my boat here. Okay, so in this case here, our methyl group is in our equatorial position, and our hydrogen is in our axial position right here. And we're going to flip it over. So we're going to draw it the other way. So it's going to be this way, that way, that way, that way, that way. And now our methyl group is in the equatorial position, axial position, and our hydrogen is in the equatorial position. And this can flip back and forth. So this is an equilibrium here. Which do you think is more stable? With the methyl group in the equatorial position or the methyl group in the axial? Okay, so let's draw that, and you're right, but now let's see why. So in this position right here, if we had the CH3 up here, we actually have those hydrogens stick out quite a bit right here. And notice those hydrogens on the methyl group are starting to hit the two other axial hydrogens on the cyclohexane. So because it's coming and butting up against this, these hydrogens here, it has more sterics on it, and it wants to push it away. So that means that the equilibrium is going to lie on having the large group in the equatorial position. Okay, so by how much? Well, let's take a look. On this table here, we're going to look at the number of the equilibrium between the equatorial and axial. With just hydrogen, it's 1-to-1. So half the time it's in equatorial, half the time it's in axial. If we take one hydrogen and sign it, it's just going to flap back and forth. And it's 1-to-1 because there's no difference in sterics between the hydrogens. If we put a methyl group on there, 18 out of 19 of those configurations are going to have the methyl group in the equatorial position. Okay, so let's add a slightly larger group, an ethyl group. Not much larger, but 21 out of 22 molecules of cyclohexane are going to be in having the methyl group in the equatorial position. So that's not much bigger. So let's to an isopropyl group. 35 out of 36 molecules are going to be in that equatorial position. And then if we go something like a big, huge T-butyl group, it's almost 99.9%. It's going to go into that equatorial position because it's just too big to stay in that axial position. Okay, do we see how that substituent size affects which conformation of the chair it's going to be? It's going to be one conformation of the chair or the other. And the conformation it's going to be is where your biggest substituent is going to be the axial, no, equatorial. The biggest substituent is going to be the equatorial position. Because the axial positions are too close, you want them in the equatorials facing out. Okay, and it even has an effect with things that are here. As we get bigger, we see that it gets a little bit more favored toward one or the other, but not nearly as much as those alkyl substituents. Okay, well, what if you have two things on the ring? Well, if you have two things on the ring, you have to figure out which one's which, right? So let's do a dimethyl first. So we're going to draw our two lines here, have that, have this here. And I'm going to do hydrogen here, methyl group here. Then I'm going to do hydrogen here and methyl group here. Okay, so in this position, we have one methyl group in the axial position and one methyl group in the equatorial position. And if we flip this back and forth, what's going to happen? So the cool thing about cyclohexanes is if you were axial in one chair configuration, you're now equatorial in the other. And if you were equatorial in one and you flip, you are now axial. Always happens. All of them flip positions. So in this case here, let me draw it, circle it in red here. This is the axial position. And this is the equatorial position. And now just by flipping it, we haven't rotated it or anything. This methyl group is now in the axial position. This hydrogen is now in the axial position. And this methyl group is in the equatorial in there. So this will flip back and forth. So is there an energy difference between these?
No.
In one case, one has a methyl group in the axial and one in the equatorial. In the other case, it has one in the axial and one in the equatorial. So these should be the same in energy, right? So let's move the methyl group. Let's make it somewhere where we might see a change. So let's draw the same one here, get in that same configuration. I'm going to put my methyl group here, CH3H. I'm going to switch these two right here. That way we have them on different sides now. So what we see here is in this one, both of these are in the axial position right here. So that means when we flip it, both of those are going to be in the equatorial position. So what we're going to do is we're going to pull this side up and we're going to redraw and put that side down. And now our methyl group is here and our hydrogen's here. Our methyl group is here and our hydrogen's here. See how those methyl groups are now both in the equatorial position? So which direction does the equilibrium rely on this one? Toward the one where the methyl groups are both axial, or they're both equatorial? Both equatorial, because those are the furthest, equatorial is more stable, and those are going to give us our better answer. Okay, questions on that? So that's just with methyl groups. What if you had a T-butyl in the methyl group? So let's draw that. Are you getting practice drawing these cyclohexanes with the two lines right here? So I always like to talk two parallel lines because then I know where to put the points. So let's put a T-butyl group here, and the hydrogen would be axial. And let's put a methyl group here, and that hydrogen would be axial. And if we flip this back and forth, we would end up having not only, let's see, we're going to pull that one up, pull that one down. So that's going to draw it like this, and then the parallel lines, and then this. And that T-butyl group is now going to be in that equatorial position, and the methyl group is going to be in the equatorial position. Okay. So what's the likelihood it's going to be in this configuration? Very, very low. But what if the groups weren't? So we have both of them turning into axial positions. Both of them turned into axial positions. Okay, those were the axials on that side. These are the axials on this side. So if we had a different isomer of this T-butyl, let's, oops, didn't draw the two lines, messed it up. Let's leave that T-butyl group here. Let's leave that hydrogen here, but let's switch this over here. We're going to have the methyl group here and the hydrogen here. Okay. So now we have the T-butyl group in the equatorial position, but the methyl group's in the axial position. So if we redraw it, we're going to see that that methyl group is now in the equatorial position, and the T-butyl group is now in the axial position. So I'm going to circle the axials again. Axial, 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 and axial. Okay, so now we have at least one of the groups there, but still, where does the equilibrium on this equation lie? It's going to lie on the larger group being in the equatorial position. So it's actually going to lie to this side here. And so on both of these, it's going to lie to where you have the highest number of groups in the equatorial position or the largest group in the equatorial position. All right, questions on that? Okay, so now we have cyclohexanes. And we like to do a lot of work with cyclohexanes because there's less free rotation. So you'll see a lot of stuff done with cyclohexanes in the future, like that. So practice on your homework how to draw those. Okay. All right. So now we're going to switch to something a little different. We're going to have our first reactions. So alkanes don't do much. So the one thing we can do is we can burn them. And when we burn them, we would just have CH4 plus oxygen of some sort. And it burns to produce CO2 and water. And let's see, to balance that out, we're going to need 2 equivalents of oxygen. And we'll generate 2 equivalents of water. Okay? So that means we're going to break every single carbon-hydrogen bond and turn them into carbon-oxygen bonds and hydrogen-oxygen bonds. Okay? So, you know, and then it's done. It's CO2 and water. So we don't do much with combustion except learn about stability of things. The other thing that can happen, though, is we can use free radicals to do substitution reactions. So if we have a hydrogen here, we can then heat it with bromine and hit it with light or heat, H nu, light or heat. And we'll do a substitution reaction where we're taking off one of the hydrogens, replacing it with a bromine, and generating one equivalent of HBr. Okay. So that's pretty cool. We're going to talk about that mechanism in chapter 10. So that's a reaction it can do is substitution. Okay, so that's about all we can do with these as far as reactions go. We can burn them and we can do a radical substitution. All right. So how do we make alkanes? Well, we actually make alkanes from other things. So one of the most common ways to make an alkane is to start with an alkene or an alkyne right here and doing an addition reaction across the double or triple bond. Hydrogen. And the way we do that is we add hydrogen and a catalyst, typically platinum, palladium, or nickel. And we can add one equivalent of hydrogen across that double bond, creating two new carbon-hydrogen bonds to give us, in fact, I'm going to draw the hydrogen here in blue. And we're going to, actually, let me do it that way. So we're going to actually go where this comes here, this goes there, and we're going to add across that double bond to generate two hydrogens across that double bond. And then the other hydrogens are still there. So this is how we can make an alkane from a double bond. It's called reduction because we're reducing it from a double bond to only single bond. And we can do the same thing with the same catalyst in acetylene, but we have to do it at least once or twice. We can do it once and get it to go to an alkene, but the alkene reacts with the same catalyst system, and so it can do it again and go all the way down to the alkane. Sorry, I need to draw these in red. Hydrogen, double bond. So the first equivalent is going to add across the double bond, and then the second equivalent adds across the double bond to give us our 4 added hydrogens across that triple bond. So the first double bond goes, and then the second double bond. So this will work with any double or triple bond. This is our first chemistry where you want to use a hydrogenation. It's hydrogen gas, H2, and platinum, palladium, or nickel. It always adds 2 hydrogens across a double bond. Questions on that? So that's all the chemistry for this chapter. So we'll start reaction tables next chapter. We'll want to add this to it. So how do we know by looking at an empirical structure, an empirical formula, whether we have rings or double bonds or stuff like that, right? When we talk about, drawing our Lewis dot structures, it's like, well, we just start with the thing in the middle and keep putting things around it. But we can actually derive how many double or triple bonds we have or how many rings we have by calculating out the index of hydrogen deficiency. It's basically how many hydrogens could you add to the system to make it into an alkane, a non-cyclic alkane. So we want to look at ways to do this. And so we need to think about, okay, a double bond takes away 2 hydrogens. A triple bond takes away 4 hydrogens. A ring takes away 2 hydrogens. So we should be able to calculate out whether or not they do it. So if we look at stuff like OH, Structure like this is citronella oil. It has one double bond. So the empirical formula should have 2 less hydrogens in a fully saturated hydrocarbon. Okay, so fully saturated means no double bonds, no triple bonds, and no rings. Okay, so to calculate out that degree of unsaturation, we have a way to do it. Okay, and if the general form of a hydrocarbon, saturated hydrocarbon, is C. Oh, so for a saturated hydrocarbon, you're going to have C to the N, H, 2N plus 2. Okay, so that's our fully saturated hydrocarbon. Okay, so if it doesn't fit this thing, so again, if we had C is equal to 3, we would have H, 2 times 3 is 6 plus 2 is 8, right here. So that empirical formula would give us a saturated hydrocarbon. But if we took 2 hydrogens away, it would not be that. So let's figure out how to do that. If we have an unsaturation, we could have, let's say we had 4 hydrogens were missing from the empirical formula. Okay, 4 hydrogens were missing from the empirical formula. So we had C4H6. So C4H6 over here, C4H would be, let's see, 2 times 4 is 8 plus 2 is 10. So the saturated hydrocarbon would have 10 hydrogens in it. We only have 6. So if we calculate out the number of hydrogens that are missing, we can look at how many bonds we have. Now, because we have 2 hydrogens missing, I'm sorry, 4 hydrogens missing, that means we have to have 2 pi bonds or 2 rings or a ring and a pi bond. So we could actually have something like this with a double bond, because the ring takes up 2 hydrogens and the double bond takes up 2 hydrogens. In this case here, each of those double bonds takes up 2 hydrogens. And we could also do it like that. 2 rings would take up 4 hydrogens. So now we can do it. It can be any of these structures, but we know that there's double bonds or rings in the structure because of the calculation. So let's do the calculation. So the calculation is 2N, and N being the number of carbons, minus 2, plus 2, minus 2, where X is the degree of unsaturation. So we're solving for X. Okay, we're solving for X. Okay, so let's do C4H6. Okay, so if we look at our 2N plus 2 minus 2, we're looking that this 2N plus 2 minus 2X is equal to 6. Why is it equal to 6? That's the number of hydrogens we have now. Okay, we know how many it should have when it's saturated, but this is how many hydrogens we have now. So now we're going to have to solve for X, and we know what N is. So we have 2 times 4 plus 2 minus 2X is equal to 6. So that's 8 plus 2 is 10 minus 2X is equal to 6. And then let's move this over here by adding a 2X to this side and both sides, and then that'll cancel out. So we'll have 10 is equal to 6 plus 2X. And if we subtract 6 from both sides, we get 4 is equal to 2X. And then, of course, dividing by 2, we get 2 is equal to our degree of unsaturation. Okay, so what does that mean? We have 2 things that are unsaturated there. So that means we have 4 hydrogens missing. Okay, we're going to have 2 double bonds. We're going to have 2 rings. We're going to have a ring and a double bond. That's what that X means. Okay. Do you want me to do that calculation one more time?
Why did you turn 6 back?
No, because I would just subtract 6 from both sides.
Oh.
So Is it's easier for me to make the X positive by moving it over. Do you want me to do that calculation one more time? No? No? Okay. Well, there's an extra calculation in the notes on Canvas. So there you go. Okay, so how do we use this? Okay, to figure out what kind of our empirical formula is. Well, we can actually use it to figure out if it has things other than carbons and hydrogens. But there's a couple rules we have to think. The first rule is we don't care about oxygens because it only bonds twice. It's not going to change our unsaturation number. So we don't care about that. We don't use that in our calculation. We're going to add the number of halogens to the number of hydrogens because they bond once, like hydrogen does. They count like a hydrogen. Okay. And we're going to subtract one hydrogen for nitrogen. Why? Nitrogen only bonds 3 times and has a lone pair. So carbon bonds 4 times, the halogens, the oxygen bonds 2 times, and we don't, it's 4 and 2, so we have to subtract 1 hydrogen when we have nitrogen. Okay, so let's calculate that out. Let's do C7H11Br. That's an easy one because we have hydrogen added to the bromine. So let's do our calculation here. We have 2N plus 2 minus 2X is equal to, let's see, we have 11 plus 1 is 12. We add the halogen to the hydrogen, right? And if we do this calculation, we have 14 plus 2 minus 2X is equal to 12, which gives us 16. And then minus 2x is equal to 12. Let's subtract 12 from both sides. That'll give us 4 minus 2x is equal to 0. Let's add 2x to both sides. 4, 2x. 4 is equal to 2x. And that means our x is equal to 2. Okay. So it's a little different with the nitrogen. We have to subtract. So with the halogens, we added it to there. With the nitrogens, we subtract. So let me go ahead and do one with that. And we have, let's see, C5H9N. Okay, so we have 2N plus 2 minus 2X is equal to 9. And it's going to subtract 1 for the nitrogen, so it's going to be 8. Okay, and so if we run through our math, we have 12 minus 2x is equal to 8. We have 4 is equal to 2x, and x is equal to 2 again. Okay, questions on that? There's a couple homework problems on that, so please go back and revisit that. All right, questions on degree of unsaturation. This is kind of really good to know, especially if you have an empirical formula that saying draw this structure, okay? And you'll have to know, okay, do I have any double bonds? Do I have a carbonyl? Do I have what? Knowing the degree of unsaturation will tell you how many double bonds you have, how many circles you have, how many hydrogens that you could fit in there. So it'll help you build your molecules better. All right, questions on that? That's the end of chapter 4. We're going to start chapter 5 now. All right. So chapter 5, stereochemistry. I told you stereochemistry is when things are fixed in space. And if they're fixed in space, that means you can have different isomers that are fixed in that space. So when we first talked about it, we talked about cis and trans isomers. And the cis and trans isomers were fixed in space because they had that no rotation across it. Okay, so we're going to talk about how things are fixed in space for things that have sigma bonds also. Okay, so one of the reasons we do this is about 61% of all pharmaceuticals have a chiral center or a stereochemical center. And so we will see this in almost all of our pharmaceuticals, most of our natural products. A lot of them have all sorts of stuff. So it's really important to kind of grasp this. And one example of that fixed in space actually changing properties is if you take this isomer here of carbone, and you isolate it from caraway seeds, it is actually one stereocenter different than spearmint oil produced in a different plant, okay? One flipping of an object in space changes it from tasting or smelling earthy to tasting and smelling minty. Your body can tell the difference between these, okay? So you need to learn how to tell the difference between these. Okay, so how do we do that? Oh, we already did that. So the first thing we need to do is talk about different types of isomers. Obviously, we have constitutional isomers, and we know that those are easy to tell apart because number one, they have different names, they can have different functional groups, they typically have different physical properties and or chemical properties. However, stereoisomers only differ in the way those atoms are oriented in space. That means they have exactly the same name except for the stereoisomer name. In this case, it's going to be cis and trans, or our new ones R and S. Those are the ones we're going to learn today. They will always have the same functional group. They will always have all of the same attachments except for that one configuration. That one bond, two little atoms are going to be swapped somewhere on the system. And they are going to be, but have all the other linkages the same. So we have different types of stereoisomers. So the first type of stereoisomer is what we call geometric stereoisomers. That's our cis and trans, okay? Our cis and trans is that geometric isomer. And we can always tell them apart because the cis and trans are in front. Okay, but then we have another one which we call optical isomers. And the reason we call them optical isomers is we can only tell them apart using a special optical technique, which we'll discuss at the end of this chapter. So in this case here, we have those two things that are identical except for their flipped in space part, are what we call enantiomers. Okay, and we'll have different names for them, and that is defined by which isomer you have. Okay, so in the case of constitutional isomers, we can see right away that if we just move one of these methyl groups over one space, we have this. That is a constitutional isomer. We have moved a bond. We have swapped a hydrogen and moved the carbon over one bond. In this case here, these have all the same connections. We did not move anything. Okay, these are stereoisomers. The backbone of this has changed, right? You've moved a carbon backbone. Here, you have the carbons hooked to the exact same things. They're just different in space. Okay, so that's the thing we're going to have to get a hold of here. Okay, so I want to describe a word, chirality. Chiral means hand, and so chirality actually means handedness. And what that means is that you have a non-superimposable mirror image of an object. Okay. So if we look at my hands here, they're superimposable, right? I'm sorry, they are mirror images of each other. But if I tried to lay them on top of each other in that same order, they do not superimpose. Okay. The molecules that we are going to be looking at are things that are going to be mirror images of each other. But when you try to superimpose them, two of the atoms have swapped every single time. So that's what we're looking for. We're looking for mirror images and that. And so you can see a lot of different things have mirror images. But what if you have a mirror image and they do overlap? Like in the case of this fork down here. If they can be stacked on that makes them not chiral. The word is achiral. A meaning not. So a chiral object is mirror images, non-superimposable. If you have mirror images and are superimposable, that's not chiral. If you don't have a mirror image, that's not chiral. So that's what we're going to do. So some examples of achiral molecules are water and this bromochloromethane. Why? Well, let me draw water for you. Right here we got that. And we have a lone pair up here, and we have a lone pair over here. So we have hydrogen, hydrogen here. So if I took that molecule, it has a mirror image, right? We can draw a mirror of it and draw another water molecule. But then if we just move this water molecule over in front of this one, they are superimposable. So that's not a chiral molecule. So let's try it with something with carbon on it. Let's go Cl, and we're gonna draw a heavy wedge is coming out at us, bromine. And then a light wedge is the hydrogen here. And then in the plane is the other hydrogen, right? So let's draw this mirror image. We have bromine on the wedge here. We have hydrogen on this wedge. We have chlorine up here, and we have hydrogen over here, okay? So we have a mirror image there, but what happens if you rotate this 120 degrees? These two hydrogens line up, the bromine lines up, they all line up. They're superimposable. So it's an achiral object, a non-chiral object. Okay. So let's talk about chiral molecules. Okay, so a chiral molecule is something that is mirror image and non-superposable. So the first rule of chiral molecule is there must be 4 different things hooked to the carbon. 4 different things hooked to the carbon, okay? If there are 2 of the same thing hooked to the carbon, it cannot be chiral. You will be able to find a way to superimpose it. So we're looking for 4 different things on the carbon, okay? So if we look at this example here, we have 4 different things bonded to this carbon, okay? And so we have the methyl group, the ethyl group, the OH group, the hydroxide, and there. So we have this alcohol. So this is butanol, 2-butanol, to be precise. Here's its mirror image right here, okay? But if we try to superimpose them, notice that the methyl group and the ethyl group are on opposite sides in those 2 different molecules. So because these are not matching, they are not superimposable. Therefore, it is a chiral molecule. Okay.
Why can't you just rotate it like
Let's
you
talk
did?
about chiral molecules. Every chiral molecule has an asymmetric center. Okay, what that means is that's the chiral center, that's the stereo center, the stereogenic center. Any of these are the same word, stereo center. So chiral carbon, I'll use a lot, and stereo center, I'll use a lot. That just means it's a stereoisomer or a chiral isomer, and that it's the thing with the 4 different groups bonded to it, okay? So when we have those 4 different groups, we have chirality. When we have its mirror image, we have the other isomer. All right. So let's see. So let's talk about the other isomer. Okay. So when we have a stereo isomers, so we're going to have one of them, and then we can draw a mirror image of the other one, and that's the other one. So these 2 make up a pair of stereoisomers because they're identical except for that difference, that non-superimposable isomer. So if we look at that mirror image and we see that they have those, we're going to have those 2 molecules make up a pair of enantiomers. Okay, chiral centers always have 4 things bonded to them, and enantiomers always come in pairs because you have the one side of the mirror and the other side of the mirror. Okay, so if we look at our compound here, we draw our mirror image of it over here, and we try to superimpose it on there. We're going to see the methyl group and the ethyl group are not going to line up. They're going to be overlapping each other. But in this one right here, notice we have 2 methyl groups. So we switched out a hydrogen for a methyl group. When we draw its mirror image, all we have to do is rotate it 180 degrees and it'll overlap. So we see how that changing that hydrogen to a methyl group is going to allow it to rotate 180 degrees and completely overlap with the previous molecule. So that means this is an achiral molecule, and this is a chiral molecule. Okay, so once we have our chiral molecule, we now have to also start looking for what we call planes of symmetry, because that's going to come into play when the molecules start getting a little more complex. So in the case of a plane of symmetry, you can find it through the center of a bond, you can find it through atoms, you can find it through rings. So what you're going to do is start identifying these things as, oh, can I put a plane of symmetry? Can I put a mirror in there and do both sides look the same? In this case here, we're looking at the plane being right through these three atoms here. And so we have a methyl group on this side and a methyl group on this side. What that means is that this side of the mirror looks exactly like that side of the mirror. Therefore, there's a plane of symmetry in there, and it's an achiral molecule, not chiral. But if we look at the one where we had the methyl group and the ethyl group here, one has an ethyl group on it, that's not a methyl group, and therefore they're different, and therefore there is a chiral center, and that's what we're looking for. So achiral materials contain a plane of symmetry. You can actually have a compound with two chiral centers in it, but you can find a plane of symmetry and it becomes an achiral molecule. We'll get to that in a minute. All right, so how to find stereogenic centers? Okay, the first thing we want to do is we want to look for 4 different things. Okay, so that means anything that's a CH2, a CH3, ignore. Those can't be chiral centers. So you have to look for anything that has those on. The other thing is it has to have 4 bonds. So you can't be sp or sp2 hybridized. Must be sp3 hybridized. Must have 4 bonds. Okay. So if we look at something like, let's see, carbon with fluorine, bromine, iodine, hydrogen, and iodine right here. Okay, we have 4 different things. That means it's a stereogenic carbon. It's a chiral carbon. Okay, let's do this. Let me draw it differently. Bromine. So is there a stereogenic center in here? Well, let me draw the hydrogen for you. Okay, so this, the carbon, the bromine is bonded to it is our stereogenic center. It's got a bromine, a hydrogen, an ethyl group, and a propyl group. 4 different groups. It's a stereogenic center right here. So that's our chiral carbon. Okay, so let's take a quick quiz. Carbon number 1, chiral or not?
Yes.
Because? Huh?
It's different on each side.
How many hydrogens does it have? Right. That's 3 of the same thing, so it can't be chiral. Chiral things have 4 different things bonded to them. The hydrogens are all the same, therefore that can't be a chiral center. The nitrogen only has 3 things bonded to it. Nitrogen can be chiral, but not in this state. So let's draw the first one, no. Not chiral. What about carbon number 2? No, for the same reason. It has 3 of the same group on it. No. And let's look at number 3. Ooh, that's a little harder. Okay, let's draw our hydrogen here just to make sure we don't forget it. We have a nitrogen, a hydrogen, a carbon that's sp2 hybridized, and a carbon that's sp3 hybridized. That has 4 different groups on it. So it is chiral. Okay, we see how to identify 4 different groups. Don't forget your hydrogens, it'll help, it helps. All right, let's look at this one right here. We don't have to add any hydrogens because we already have 4 bonds to there. Let's see, we have an sp2 hybridized carbon, an sp2 hybridized carbon, an oxygen, and an sp3 hybridized carbon. Okay, we have to dig a little further. Is this carbon exactly like this carbon? No, because they both have oxygens bonded to it, but this is double bonded to the oxygen. This is only single bonded to the oxygen. So they're different. So it's chiral. Okay, let's look at 5. Chiral or no? No, because it's a methyl group. No. Let's look at 6 here. Okay. We have an oxygen, an sp3 hybridized carbon, an sp3 hybridized carbon, but different. It's not a methyl group, and an sp2 hybridized carbon. Is it chiral? Yeah. Yes. All right, are we starting to see this? We can start to see that any difference is going to make a difference. All right, let's look at number 7. We have a carbon here that's different than that carbon. We have a hydrogen here, and we have an sp2 hybridized carbon. So we have 4 different things. So it's chiral. Let's see, 8. All right, what is 8? Yes or no? Let's
No.
draw our hydrogens in. Got 2 hydrogens on it, can't be chiral, so it's a no. And let's look at 9, the last here. So let's see. All right, this carbon is different than this carbon because that one has a nitrogen on it and that one has an oxygen on it. And this doesn't have either one. And then the hydrogens are 4th group. So it is chiral. There we go. All right, do we see how to identify chiral centers now? You're looking for the 4 different things, and then we can start assigning them their names and structures. Okay, so how do we draw our stereoisomer? Okay, so the first way to draw our stereoisomer is to get it in the stereocenter in that 3-dimensional drawing where it's wedges and or dashed wedges and lines. Okay, so we have to get that wedge drawing first. Then we want to, we can put them anywhere we want. It doesn't matter. We just have to get in that wedge structure. And then we draw the mirror image. So let's see, we have this structure here. This is butanol. So I'm going to put the OH up here just because I want to. I'm going to put this ethyl group here in the plane of the page. And I'm going to draw, let's see, the methyl group is going to stick out at us with this dark wedge. And then this dashed line is our remaining hydrogen. Okay. So how do I draw the mirror image? Well, the easiest way to draw the mirror image is to start from the mirror and work your way out. So the first thing I see is a CH3. And it still has a wedge right there. Then we have a hydrogen, and it has a dashed wedge. We have our OH, and then we have our ethyl group. Start from the mirror and draw out. Don't try to just like rotate it and do anything like that. If you do it from the mirror, you're going to get the structure more often than not. Okay, so that being said, do we know how to draw enantiomers now? We still haven't figured out how to name them. We know they're different, but we're going to get to that later. Okay, so what happens if you have 4 different things in a ring? Maybe you have a stereogenic center in a ring, okay? So if we look at this right here, is this a stereocarbon? Is carbon 1 a stereocarbon? Let's look. All right, how many things do we have on here? We have a hydrogen here, we have a methyl group here, then we have a carbon, but that's kind of like this carbon. So let's go out again. Carbon, now that's like this carbon, and oh, we ended up going to this carbon and that carbon. So it turns out both of those groups are identical because the more you go out, the more they're the same. I mean, you can go out, you can go around the ring several times and it's all going to be the same. So what we also see here is that we can actually draw a plane of symmetry in here. If we drew the plane of symmetry in the plane of these molecules here, both halves of that ring are on both sides. They're mirror images on each other. And so the ring of symmetry actually cuts straight through the plane of the cyclopropyl group. So if we look at this one here, we've broken up the symmetry by adding a new functional group here. So we have a CH2, a CH3, an H, and then this is a CH. 4 different groups. We now have a chiral carbon. And if you try to draw that same plane here, you're going to have a double bond on one side and a single bond on the other. It does not have a plane of symmetry. Therefore, it is chiral. Okay, so 4 different things, no plane of symmetry. 4 different things, no plane of symmetry. All right. So now we figured out how to get there. Let's figure out how to label it. Okay, we're going to use a rule. Engel something, I forgot the acronym, but it's CPI rule. So we're going to figure out how to label the one mirror image and the other mirror image, because the only thing that's going to be different in their names is an R or an S. Okay, so what we'll want to do is we'll want to assign 4 rules to give us our priorities, and then that priority is going to tell us whether we have the R or the S isomer. So our first rule is atomic number. Now notice it says number, not mass. So let's draw this here and fluorine. Okay. So by atomic number, which of these is the highest? Okay. So the highest priority is the one with the highest atomic number, which is going to make this. Let me change colors here. This bromine is going to be number 1 because it's the furthest down the list. It's number 35. And then we have this one. This is number 17, sorry. And then this is 9. So this is 3. And this is 4. So we've assigned our priorities based on atomic number. Okay. Now, what if we had 2 carbons attached to this? Okay, well, we need to do something else. Okay, the greater the atomic number of the atom bonded directly to the stereo center, the highest priority, right? So our priority goes by atomic number, and I'll do a different one here. CH3, hydrogen, chlorine, and bromine. So on this one right here, we would have 1 for the bromine, 2 for the chlorine, 3 for the carbon, and 4 for a hydrogen. Hydrogen's always going to be 4, by the way, because it's the lowest number. So what if we have a slightly more complex? Let's draw that same thing, but different. Let's draw it as 1 Cl and then CH3 and then CH2 and then CH3 and an H back here. So wedge here, wedge here. Okay, so we have to go and start prioritizing. So number 1's chlorine. Number 4 is going to be the hydrogen. Carbon. Okay, this carbon and this carbon are both 6. What do we do now? We look at what's attached to that carbon, okay? So in this case here, we have a carbon that's attached to a hydrogen, and a hydrogen. Okay, and each of these are atomic number 1. We have this carbon is attached to a hydrogen, and a carbon. So this is a 1, and a 6. Okay, which one's higher priority? The one that has the higher atomic numbers attached to the thing we're talking about. So this right here is the higher priority because it has the other carbon bonded to it. This has nothing but hydrogens bonded to it, so it has a lower atomic numbers attached to it. Therefore, it is going to make this number 2 and this number 3. Okay. Do we see what that second rule is saying? Okay. You go out until there's a difference. The one that has the higher atomic number in the difference is the higher priority. Okay. So the next rule is, what about bonds, double bonds. How do we count double bonds? Well, we count them by, let's see, let me draw them. By, you count each bond to that atom. CH3 as a priority. So we have number 1 up here again, number 4 back here. So we have the 2 carbons. So we have the first carbon here. It's carbon bonded to 2 hydrogens and a carbon. So that's pretty easy. That's the rule we just used. But how do we do this carbon here? We have a carbon. It's bonded to 1 hydrogen from here. It's bonded to carbon once with the sigma bond. It's bonded to carbon again with the pi bond. That means we have to count each bond to that atom, and that atom counts. So now we have 2 carbons over here, only 1 carbon over here. So it's the higher priority. The higher priority. So that makes this our 2 and this our 3. So you see how that works. If you had it double bonded to an oxygen, you have to count oxygen twice. If you have it triple bonded to a carbon, you go carbon, 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 and that would count. Okay. All right, does that make sense? You count each bond to that atom and write that atom. The last rule we don't use very much, but it is true that if you have different isotopes, the heavier isotope wins. Okay, because all the isotopes have the same atomic number, you can't do it by number. Because they're all the same atom and they're not attached to anything, you can't do it that way. So you have to do it by the mass of the atom. So we hardly ever use that one, but it is true, and you will see it. All right. So let's assign some priorities. Okay, let's do bromine, CH3, CH2, iodine, chlorine, and hydrogen. All right. Let me CH2 iodine. Okay. All right. So iodine's the heaviest one there, so it's priority 1, right? No, it's not attached to our chiral carbon. We have to look at our which carbon's chiral first. This is our chiral carbon, so we're only looking at the things attached directly to it first for atomic number. So rule 1 has to be attached to that chiral carbon. So that makes this number 1 and this number 2, because bromine is higher atomic number than chlorine, and chlorine, this one is 3. Even though it has this iodine attached to it, that iodine is not attached to the chiral carbon. It doesn't count in prioritization unless we had a CH3 over here. We have a CH3 over there. This iodine is different from one of these hydrogens. It's heavier, higher number than the hydrogen, and it would become part of the rule, and we would use it. And then this, of course, would be 4. All right. So let's try another one. Let's do that one. So the first thing we do is identify our chiral center. And this one, it's this one right here. Okay. So let's do our thing. Okay, so this right here is going to be a CHHH. Okay. This one right here is going to be a C. This C right here is a CHH. Right here. This one here is going to be this carbon has a carbon, a hydrogen, and a hydrogen. And this last one here, this one right here has, let's see, a carbon, and a hydrogen. Okay. So what's the highest priority of these carbons? It's going to be the ones with the 2 carbons on it. So that's going to put this as a priority 1. What's next? Is it the ethyl group or the butyl group? Okay, so they're the same here. If we're looking at these, and these numbers are exactly the same. So we have to go out one more. And if we go out to this one and this one right here, this is going to give us a C with an HHH on it. This is going to give us a C with a CHH on it. That makes this priority. So this is going to be 2. This is going to be 3, and this is going to be 4. Okay, so we see how to do the prioritization. Oops. There we go. All right, question. Why can't you rotate the alcohol if you did previously? Why can't you rotate the alcohol? I'm sorry, I don't know where that was. It was on the previous one. You can rotate it, but it's not going to overlap. When you're drawing it mirror image wise, it's better to use the mirror plane to do it. All right, let's do one more example. I'm going to do it down here. I'm going to start with this. All right. So what's first? Well, oxygen's higher than carbon, so I'm going to say this is number 1 right here. I'm going to say this is going to be number 4 because it's a hydrogen. So let's look at the first one here. Let's look at this carbon. So it's carbon and it's oxygen, oxygen, hydrogen. Let's look at this one here. Carbon, oxygen, oxygen, carbon. Which one's higher priority? The aldehyde or the ketone? Ooh, functional group test. Which one? So this has a hydrogen on it. So this is the aldehyde with the hydrogen on it. This has a carbon on it. This is the ketone. So the ketone takes priority. The ketone takes priority because it has the 1 atom. It's a higher atomic number. All right, questions on that? Okay, so now that we have our priority down, we can draw our structure in 3D. We can use a mirror to draw its enantiomer, and now we can prioritize to get us to our next rule. Okay, our next rule is assigning R and S. Okay, so when we assign R and S, we look at it such that we get the first 3, 1, 2, and 3 position in a perspective where we can see whether they're going in clockwise order, 1, 2, 3, or counterclockwise order, 1, 2, 3. Okay, so what I mean by that is if I had my structure here, let's just do general structure where we have 1, 2, 3, and I'm going to put 4 back here. And I'm going to draw the mirror image of it just to make sure we're doing it right. And 3, and 1, and 2. Okay. We see how I drew this mirror image of that just by going out from the middle? Okay. So now let's look at the first one. Priority 1 is at the top. Priority 2 is on the left, and then priority 3. So if we're going to follow those around in order, we're going to see 1, 2, 3. And is that clockwise or counterclockwise? That's counterclockwise. So this is going to be our S isomer. It's our S isomer. S stands for sinister, which means left, old Latin term. R stands for rectus, which means to the right. So now let's do this one. We have 1, 2, 3. So now this one's going clockwise. So this is our R isomer. Okay. So when you look at your prioritization, you need to be looking at the 1, 2, 3 and have your 4 away from you. And if it's going clockwise, it is R. If it's going counterclockwise, it's S. So I want to show you a good way to do this. Okay. In fact, I want to start with, let's start with that. Okay. When we have it right here, I like to use my hand. Either hand will work, because what you're going to do is you can always adjust your hand to the drawing and then get your perspective right. So what I'm going to do is I'm going to show you how to use your hand in this structure here. So what we're going to do is we're going to assign 1, 2, and 3 to the first 3 fingers here and thumb, and 4 is always going to be our wrist. Okay, that way when we look at here, 4 is always away from us. Okay, so let's look at our fingers, look at the structure here, and if we look at that, the 1 is sticking out at us. So it's sticking out at us, so it's where my thumb is. The 2 is up here, and then the 3 is over here, and the 4 is back here. So just looking at the structure we have on the screen and doing that, the thumb is 1, 2, 3, 1, 2, 3, and we look at it now, and it's going counterclockwise. So is that RRS? Yes. Yes. All right. So now let me make it a little harder. Let's do 4, 1, 3, 2. This is going back. This is coming out at us. Okay, how would we do that? Okay, the way we do that is we'd say, okay, this is 1, this is 3, this is 2, and 4 is back here. So 1, 2, 3, 1, 2, 3, 1, 2, 3. It's counterclockwise. It's also S. So anyway, I'm going to stop there. We're going to go practice that. We're going to continue this on Wednesday. Our quiz on Wednesday is up to prioritization. So practice your prioritization. I won't do RNS just yet. We're going to do some more practice. We're going to do some more practice. All right, I'm going to go ahead and stop sharing, and I'll see you guys at home sooner or later. All right. In the